I will try to work through the problem. So let's get started with our aliquot. Let me get my little finger pointer here going here. All right, so in this case, and this is a traditional solid-solid aliquot, I'll remind you, there's solid-solid, there is solid-liquid, and liquid-liquid. They work similarly, but a little bit of differences, and certainly there are endless practice problems for all versions of that. This is our traditional solid aliquot, the way we do it, where in this case we want to weigh 45 milligrams of a drug, but using a balance that where we don't want to allow ourselves more than a 2.5% error with a balance with a 4 milligram sensitivity requirement. So can we do that? What's the least amount we can weigh on that? So I will give you the formula. You don't have to memorize the least weighable formula. I'll give that to you. The sensitivity requirement times 100 divided by the acceptable error. So in this case, 4 milligrams times 100. 400 divided by 2.5 gave me 160. So that's the least I can weigh. So 160 milligram is the least I can weigh, but it's not the amount that I need. So again, if we want to do it kind of the traditional way here, let's start with the amount of drug we need and say drug needed is 45 milligrams. The least weighable is 160 milligrams. So these are the first two things I need to identify. Now that I do that, make sure you know this formula because you need to know how to do this. I won't give this formula on the test. Your idea is to know how to calculate a multiplication factor. Is to simply take the least weighable quantity divided by the amount the drug that you need, all right? So least weighable quantity divided by drug needed will give you a number, okay? And you need to round it up. If it's a whole number to begin with, you're fine, but if it's a fraction, you need to round up. Do not round down. So 3.55 in this example will be rounded up to 4. So that's our magic number. So to figure out the amount we actually have to weigh, let's take the drug that we need times that number. So again, 45 times 4 means I can't weigh 45. I'm actually going to weigh 180. So I'm going to weigh 4 times what I need of my drug. All right. To determine then the amount of mixture, I need to determine the least amount I'm going to weigh out at the end, which can't be less than my least weighable quantity. So it's the least weighable quantity. So take the least weighable quantity. So remember, this was drug needed here. This is my least weighable quantity. So now take that times the same factor, and again, my total mixture will be 640 milligrams. So if everything mixed together is a total of 640, and 180 milligrams of that is going to be my drug, just subtract. From the total, subtract the amount of the drug, and the difference is 460 milligrams, and that's the final answer here. And again, you can do this check by showing that I show on my work here, but let me kind of show you another visual way. Okay, so this is something it's maybe a good idea to kind of think about doing because do you remember we just did this to come up with the multiplication factor? That's the formula for the multiplication factor, least weighable quantity divided by drug needed. Okay, once you know that, rewrite that same exact formula, 160 milligrams over 45 milligrams. That's exactly what we did. But now multiply the numerator by the multiplication factor and the denominator by the multiplication factor. Once you know the multiplication factor is 4, go back and say 160 times 4 is 640. 45 times 4 is 180. And knowing that on the top is the total and the bottom is your drug, then just subtract the difference. So 180 minus, from 640 gives you the 460. So I'm just trying to show you a visual way of maybe trying to remember how to do this. But it helps if you still know what each of it means because the least weighable quantity times the multiplication factor is the total mixture weight. The drug needed times the multiplication factor is the amount of drug you're going to weigh. So from the total, you subtract the drug and you get the diluent. All right? So in the end, it's 460. So hopefully that remembers that a little bit. All right, I was surprised some of you were struggling a little bit with this one, and this is a chapter 6 types of question. There is an endless practice problem that goes through just like this, so definitely practice this if you had any issues with this. So again, we're going to go through each of these ingredients and calculate the weight of the ingredients we need based off of the ingredients that we have. So let's just kind of go through that. If we start with urea, it's pretty straightforward. The prescription calls for 8% weight per weight. Again, it's a cream, so its final amount is going to be a weight, so we want the weight of the drug and the weight of the cream. So let's start with the 480 grams that we're making. We want it to be 8%, and I can't imagine how many times I've said this. Remember, 8% weight per weight is 8 grams of drug per 100 grams, in this case, of cream. So again, you'll notice I put urea drug here. In total, I could have written as cream as well. But once I multiply that out, then I get the weight of my urea. So 480 times 8 divided by 100 gave me 38.4 grams of urea. Okay, and that was the most straightforward calculation. Now the nystatin, but it all starts the same. The amount of nystatin will be based off of how much am I making. I want a cream that has a total weight of 480 grams. So that's my total weight of cream. How much nystatin do I want in my cream? I want it to have 100,000 units for every gram of cream. So 100,000 units per gram of cream will convert, if I multiply that over, from grams of cream to essentially units of nystatin. This is how many units of nystatin I want in my final product. How am I going to get it? I am using a powder that contains 1 million units per gram. And since I want to convert from units of nystatin to the grams of the powder that provides that, I multiply with 1 gram on top and 1 million units in the denominator so that units of units cancel, and I'm in grams of my powder. When I solve that away all the way across, I determine 48 grams of this powder will provide all of the nystatin units I need to make a 480 gram cream. Going backwards with that. Does everyone see where these came from? I mean, this comes from the concentration in the prescription. This comes from the concentration of my ingredients. Set it up so that in the end I know how many grams of powder will provide my nystatin. Okay? The next one, which is I think probably the trickiest of the bunch, is just the benzalkonium chloride. Once again, though, the amount we need is depending on how much we're making, and we're making 480 grams of this cream. Here is the chapter 6 thing to make sure that you're okay with the ratio strength. Don't make it harder. 1 to 10,000 in a weight per weight means 1 gram of benzalkonium chloride for every 10,000 grams of this cream. That would be the concentration, 1 gram of benzalkonium chloride for every 10,000 grams of cream. So if I multiply that times the 480 grams of cream cancels, and I'm in grams of benzalkonium chloride. That's how many grams of that I need. What's my source? Unfortunately, it is not a bulk powder, it's a liquid. It's a liquid that has a concentration of 0.5% weight per volume. That's 0.5 grams per 100 mils. So if I multiply that for 100 mils over 0.5 grams, I can convert from my grams of benzalkonium chloride to the volume of this solution that provides it. So that's the volume I need. But keep in mind, the question wants to know the weight in grams of that solution. So I need to restart with that. So I'm going to bring that down to here and say, okay, if I need 9.6 milliliters of that solution, how much will that weigh? Well, that's where I'm going to use my 1.15 specific gravity, knowing that 1.15 grams per mil is specific gravity. So if I multiply that, mils cancel, and I determine the weight of that benzalkonium chloride solution. So this is what I'll actually measure when I make this, but I need to know how much it weighs at the end. You're going to see me have to use that 11 grams here in a little bit, okay? But that's why we need to know it. Let's see, the second last thing simply wants to know, okay, the mineral oil, you said 15 grams, but I'm going to measure that out by volume. So let's take my 15 grams and use the specific gravity, but now, remember, it's 0.88 grams per mil. So to convert grams to milliliters, I have to divide by the number. So again, 15 divided by 0.88 to convert 15 grams to equivalent 17 milliliters. So again, this is the amount I'm going to actually measure since it's a liquid, but this is the weight that it represents. I'm going to have to know that here again. Okay, so the only point to this question was setting up my specific gravity in a way that the units cancel. All right. The last point to that is simply for the eucerin. How much eucerin? Well, remember, I want 480 total. Subtract everything else. So just from the total, subtract, but this is where the trick comes in. Subtract the weight of the urea, the weight of the nystatin. That was pretty straightforward, but this is where you have to subtract the weight of the benzalkonium chloride solution. Even though you're going to measure it by volume, you need to account for its weight. So we subtract the 11 grams. And again, for the mineral oil, we ignore the 17 mils we're going to measure and subtract the 15 grams that it weighs. And once you subtract all of those weights, then the weight of the eucerin that we actually would measure would be 367.6 grams. Okay, do? All right, so let's go on to, this is a chapter 8, I think, question about dosing, and in this case, body surface area dosing. Made a little more difficult because, again, if it was just body surface area dosing, this would be pretty straightforward. We would simply have to calculate a body surface area and then multiply by the dose. But this says for this drug, which is a chemo drug, it can be easily toxic, and so weight is a component of the body surface area, but what if they're obese? If they're obese, then that would maybe give us too much of a weight to account for. So they're saying if the patient's obese, do not use their actual body weight, instead use their ideal body weight. So if obese, use ideal body weight. If not obese, just use their regular body weight. That's the only trick to this question. So before I can actually calculate body surface area though, I need to know if they're obese or not. And the measure of obesity in this case would be the body mass index. And when we measure that, anything value greater than 30 would be considered obese. Therefore, we'd need to use the ideal body weight. Anything less than 30 would be non-obese. We could use their actual body weight to calculate the BSA. So far, so good. And then it's just a regular dosing thing after that. So we got two different patients, and I'll just quickly, I'll spend a little more time on patient 1. They all work the same way. In this case, patient number 1, who's 54, who weighs 220 and stands 5 feet 10 inches tall. Let's just start with determining obesity status. So let's take their weight and take 220 pounds and divide it by 2.2 to determine their actual body weight to be 100 kilograms. The 5 feet 10 inches tall is actually 70 inches. Converted to meters, using the conversion I give you to meters, is 1.78 meters. All right, so these are the actual values for this person. We went ahead and did that so we could put them into the BMI formula, and remember to square the denominator. I would tell you on this exam, remember to be careful. Either we're doing the square roots for the BSA, but in this case, making sure you square the denominator. So 100 kilograms divided by 1.78 squared gave me a value of 31.6. So when I evaluate that BMI, that's greater than 30. I'm going to consider this patient obese. So before doing the BSA calculation, I need to determine their ideal body weight, which is 50 kilograms plus 2.3 times each inch over 5 feet. They're 10 inches tall, so 2.3 times 10 is 23, plus 50 gives me their ideal body weight at 73 kilograms. So that's the weight that I plug into my BSA calculator, along with their height in centimeters. So again, 1.78 meters is 178 centimeters. Carefully do the math. You can see I took 73 times 178 first and made sure that that number was right. Then I took that numerator and divided it by 3,600 before I did anything else, and that's where I got my 3.61. Then I did not forget to take the square root of that. So in the end, my BSA was 1.9. All of that work just to get to that number. But now that I know the patient's BSA, I can calculate their dose because I can start with that, use the fact that it was 500 milligrams per meter squared. That gives me the dose. And then the only other trick, and I'll back up one step here, but there was a little bit of a trick here, is that I gave you the concentration in grams per milliliter. So 1 gram per 20 mils. Be careful, that's a gram there. So when you go to actually calculate the dose here, it's in milligrams. So remember, I multiplied by it for every 20 mils. There's 1,000 milligrams. So that milligrams cancel, and I got 19 milliliters. All right. For the sake of time, I won't belabor part 2 of this question. You can see it works the same way, except for this patient ended up being non-obese, so I used their actual body weight in the BSA formula. I did not have to calculate their ideal body weight. That's the only other difference in terms of the procedure for doing that. Okay, so let's do some pain management here. So this is opioid conversion charts. We have a 40-year-old female patient who weighs 132 pounds, taking 2 tablespoonsful of this hydrocodone acetaminophen combo at 10 milligrams per 325 per 15 milliliters. There's my concentration. She's doing that every 6 hours around the clock. The doctor is going to discharge her from the hospital and wants her to be converted to tramadol, an extended release tramadol, once daily at one of those 3 strengths. So which strength would be an equivalent dose for her, though assuming a 30% reduction in dose due to cross tolerance, going from hydrocodone to tramadol. She may be more sensitive to tramadol, so we need to back the dose down by 30%. All right, so how do we do that? we start by just calculating the dose. So the 2 tablespoons here, let's start with that. 2 tablespoons times 15 mils per tablespoon gives me the volume of 30 milliliters. Okay, times 10 milligrams per 15 milliliters. All right, basically gives me 10 milligrams, I'm sorry, 20 milligrams times my 4 doses per day. Since they're doing it every 6 hours, I converted that to 4 doses per day. And that converts then to, that milligrams per day is what you end up with. And that gives me 80 milligrams per day of hydrocodone. Not sure I did a great job explaining that, but if you do that math all the way across, she's getting 80 milligrams at her current dose. All right, that's per day. Let's go ahead and convert that to tramadol. So what I'm going to do is start with my 80 milligrams here, but let's go over to tramadol. Let's go to hydrocodone first. Here's my hydrocodone equivalent. So for every 30 milligrams of hydrocodone, that is equivalent to 120 milligrams of tramadol. Remember, all of these numbers are equal to each other. So we just get the ones that match, and these are all oral. So I know my conversion is for every 120 milligrams of tramadol, equivalent to 30 milligrams of hydrocodone. So when I divide by 30 and multiply by 120, I end up with 320 milligrams per day of tramadol. So should we go ahead and give her the 300 milligram capsule? The trick is, what have we not factored in yet? The 30% reduction. So remember, we're not going to multiply by 0.3. If it's a 30% reduction, how much has to still be there? 100 minus 30 is what? 70. So we're going to multiply the dose by 70%. We need 70% of the equivalent dose, which reflects the 30% reduction. So 70% of 320 is where I came up with 224. And remember, in these calculations, we always tend to round down to be safer. So obviously, we're going to go from 224 down to 200 milligrams PO once daily. All right. So I guess the biggest part is, are you familiar, do you remember that? This idea of using this table here to come up with your conversion to go from one to the other, and then don't forget about the reduction. All right. Now, this next question just drives on and say, okay, let's adjust it for renal function. So let's calculate this patient's renal function. She was 40 years old. She weighed 132 pounds, and now we know her serum creatinine is 2.53. So I will provide you this formula. That's not the problem. So let's calculate it. Again, the age goes in here. Her 132 pounds converted to kilograms goes here. Her serum creatinine goes down here. And if I multiply that all out, I get 33 milliliters per minute. This is bad. Why is that the wrong number? Because it doesn't affect whether her gender. So again, for female patients, remember, you've got to take that and multiply by 0.85 once you do that amount of math, and it makes a difference. So instead of 33 for a male, it's 28 because she's female. And you'll see that makes a big difference in the recommendation here in a little bit. So knowing that she's 28, that means she's less than 30, meaning that we don't want to use extended release. That would be bad. We want to use immediate release every 12 hours and not exceed 200 milligrams per day. So let's do 100 milligrams every 12 hours. So immediate release, 200 milligrams every 12 hours would give us the 200 milligrams per day max, dosed every 12 hours. All right. All right, so let's move on for the last two questions here. Our isotonicity. And again, there are practice problems for this. I'll just say this. This value, you're going to just always look for these and decide, what did I give you? I will either give you the sodium chloride equivalence, and you have to use that method, or the freezing point depression method. In this case, E means which system is that? Sodium chloride equivalence. So in this case, I want to know how many milligrams of this boric acid. See where it says QS? I need to know how many milligrams, and the number of milligrams will be based off of whatever it takes to make the final solution isotonic. All right, so let's start with this. Let's determine the tonicity sodium chloride equivalent produced by the amikacin. So if I start with amikacin, I know that I'm going to start making 90 milliliters. That's the volume I want to make. Here's its concentration. So at 90 milliliters times 2.5 grams per 100 mils will convert into the actual weight of amikacin that I need. Let's go ahead and convert the weight of amikacin to the weight of sodium chloride. Remember, E equals 0.108 means 0.108 grams of what? Sodium chloride. The number goes with sodium chloride per gram of drug. So that's why when I multiply by that, gram of drug cancels and I get grams of sodium chloride. So I do that for the amikacin. Let's do this for the diclofenac. Remember, its concentration is 0.1. So that's where if I multiply by that, I'm in the weight of the drug. If I use its E value and multiply by its E value, I go from the weight of the drug to the weight of the sodium chloride it is equivalent to. The next step would be to take the total volume I'm preparing, 90 mils, and to figure out how much sodium chloride would make it isotonic. And this is a memorization thing. What do we have to memorize? What is an isotonic concentration of sodium chloride? 0.9%. So you know that. So if I have 90 mils and I want to make it isotonic, I want to multiply that by 0.9 grams per 100 mils, meaning this is my target. That's how much sodium chloride I need. So from the total, let's subtract the amikacin, subtract the diclofenac, and what's remaining is what I still need to get. So I still need the equivalent of 0.55 grams of sodium chloride. So let's start with that since that's my target, and let's use the E value for boric acid down here. But remember, now I have to reverse the units here because I want to go from grams of sodium chloride to grams of boric acid. To do that, I've got to take for every 1 gram of drug, there is 0.52 grams of sodium chloride. So if I divide by the 0.52 and then convert grams to milligrams by multiplying by 1,000, I can see that the milligrams of boric acid I need is 1,058 milligrams. All right? I'll try to do this one quick. Same idea here, but now using the freezing point depression method. So let's start with the drug. And this one does work a little bit different here. Remember, the 0.1 is how many degrees of a reduction you get with a 1% concentration. So we're at a 1% concentration here. So 0.1 over 1, so I just set that up as a ratio. Set that equal to what concentration do I want? I want a concentration of 1.4. So X over that means I'm solving for how many degrees reduction I would need to get a 1.4% concentration. So basically by having that much drug, I will get a 0.14 degree reduction. Here's the other memorization thing for isotonicity. What is the freezing point depression of an isotonic solution? 0.52. Again, it's a negative when you do it for real, it's 0.52. So from my target, subtract what my drug is going to cause and see that I still need 0.38 degrees reduction still. What am I going to use to get that? I'm going to use glycerin. So let me use this factoid from glycerin, set it up the same way that I get 0.2 degrees for every 1% of glycerin, set it up now over the amount I need over some concentration, and I solve and get 1.9%. That's what concentration of glycerin I need to have my reduction in freezing point. All right, so if that's my concentration and I'm making 60 mils times that concentration means I need that many grams of glycerin. All right, so I need 1.14 grams of glycerin. However, it is a 30% solution. I know you're all getting ready to go, but to convert the grams of glycerin to mils, I basically multiply by 100 mils over 30 grams. That gives me finally the volume of glycerin that provides that weight, that provides that concentration. So to get the amount of water I need, let's take my total of 60 again here, subtract that amount of glycerin, and the difference is 56.2. All right.